9 o'clock, yeah.
Yeah, okay, sir.
Already he is now at 10:30 p.m.
Yeah.
Late night.
Oh my God.
We should not.
Yeah.
Okay, okay.
So, a good day, all. It's my pleasure welcoming our speaker, Dr. Krish Narendra, CEO and Technology Lead of Electric Power Groups. I welcome our advisor, Dr. G. Sambandhan, and all the participants for day 4, first session. Hope you all enjoyed this session. I would like to thank our speaker, especially spending his valuable time during this late night. So welcome you all. Welcome you, sir. With this, I would request our advisor to introduce and welcome our speaker. Over to you, sir.
Thank you, Dana. Good morning to everybody. Good morning, Ms. Dr. Krish Narendra. I have pleasure in introducing Dr. Krish Narendra, the Chief Operating Officer and Technology Lead in Electric Power Group, EPG, California, United States of America. He has over 28 years of experience in power system protection, monitoring, control, and analysis. He has expertise in innovative design, implementation, and commercialization of protective relays and disturbance monitoring recorders using advanced DSP technology on embedded systems and in Windows development environments. Skills spans power system disturbance analysis, protection, synchrophasor technology, PMUs, microgrid protection, subharmonics in power systems, sub-6 synchronous resonance, SSR, ferroresonance, HVDC controls, neural networks, artificial intelligence, fuzzy logic, and application of IEC 61850 protocols for digital substations protection and control. Dr. Narendra has been a valued IEEE member for over 15 years. He is actively participating in the IEEE PRSC working groups and is a member of PRTT of NASP. He is also a member of SIGRE Paris. He is a member of SIGRE Canada group and C4B5 working group and the NERC SMS committee also. He has published a lot of over 50 publications in various IEEE and IEC journals and conferences, and is an innovator of several patents. Now I hand over the platform to Dr. Krish Narendra. Sir, to you.
Okay, thank you very much, Sambandhan. I believe I have to cut off my video, as I said, because of the bandwidth issues, and hello to all the participants, and thank you very much for attending this session. Hopefully, I will try and do my best to make sure that this technology, whatever we are trying to accomplish here, will be presented to you in such a way that you will learn something today. And with this, I think I will shut off my video and then, the video and then start the audio of my talk. And as Mr. Sambandhan said, this technology, synchrophasor technology, I started in year 2003, implementing first time on the digital fault recorders in North America. So that was the first time a PMU was implemented on a digital disturbance recorder. And we are into this research and development topic, which is today what I'm talking about is the real-time inertia monitoring using synchrophasor technology. So I'm assuming that most of you know what are synchrophasors, but when there is a particular slide about synchrophasors, I will also discuss what it means and so on, because that's a whole lot of different topic actually all by itself. And I am assuming that we know the synchrophasor technology, and the real time here specifically refers to the continuous monitoring of inertia of the system. And then we are using synchrophasor technology to measure the real-time inertia and monitor that. And let us see why we have to do this. First of all, why do we require actually to monitor the, the inertia in real time. So the outline of my presentation essentially talks about how the inertia impacts the power system's performance and how does it affect the current regulations. For example, I'll be talking mostly about North American Reliability the corporation, which is called as NERC, and their guidelines. Actually, it is similar to what you have in CEAA or some other equivalent organization in India, where they have the regulations for electrical utilities. So, and then we'll also discuss things such as, understand the inertial response and the specific audience, or for example, the people who in the electrical industry who are interested are system operators, who are really concerned about inertia, and system planners are also concerned about inertia in a system. And then obviously protection engineers are also are concerned about the inertia and its ability to support the system. And in this talk, we also look at the synchrophasor data, which is why synchrophasor data is suitable for such a measurement. And we'll also discuss a couple of approaches, actually methods that we are doing, at Electrical Power Group to come out with the case studies, and two interesting methods I'm going to discuss actually, which is the moving window method and system identification method. And then we will summarize and have some time for question and answers. And before we really get into the inertial, real-time inertia measurement, I would like to explain, what is inertial response of a synchronous grid. So this is with respect to, the synchronous grid means it's the entire electrical system, AC electrical systems, when they are interconnected and when they are exchanging electrical power. We know as fundamental electrical engineers, you need to make sure that the frequency is within a tolerance limit. The voltage must be in a tolerance limit, basically. And the difference in phase angles, must be in tolerance limit in order for the system to be synchronized always. Now, when the entire system is synchronized, for example, India, as of now, is one big synchronous grid because it has only one frequency of operation, which is 60 Hertz, basically. Now, India is a big synchronous grid. Now, when it has a synchronous capabilities, what happens is, as you can see, the entire phenomena of electrical system happens with this equation, which is defined, as the dynamic equation, which will always be holds good because of variations, in small variations in the load and the generation. And as you could see, the difference in the mechanical and electrical power input has to be balanced by the dynamics of the system. And now what we mean by inertial response specifically is that in electrical power systems, for first few seconds, for example, up to 10 seconds or less, depending on the governor settings of the electrical systems, nothing will be supported in the system when a frequency, drops, then or the frequency goes up. Either one of the phenomena happens. Now, why does this happen? This happens because, if you lose a lot of load in electrical systems, so electrical load, when it is gone, then the generators, which are synchronously connected, they try to speed up, and therefore the frequency goes up. Now, when the generation goes off in a electrically synchronous grid, when the generation is off and the load remains same, so in order to provide a lot of load with lesser generation, the speed of the generators will come down and hence the frequency drops. Now, when this phenomena happens, because of the rotational kinetic energy that is stored in the rotors of the synchronous machines, It can be motors, it can be condensers, it can be synchronous generators. All the rotating machines which are connected synchronously have a capability of having inertia in them. And then this inertia will be utilized later on to either support the power that is lost in the grid, basically, or it can essentially acceleration or deceleration can happen depending on whether the load is in excess or generation is in excess. So what happens in this situation, what it is shown in the graph, we have a region, which is this region basically is the region where the frequency falls freely. That means there is no support from any control such as governors or frequency control methodologies, primary or secondary control, tertiary control of frequency. Nothing happens in the system. So therefore the frequency falls freely. This particular time frame is called as inertial time frame. So inertial time frame is the time frame where the only support that is available to the grid is because of the rotational kinetic energy that is stored in the system will be given back to the systems to arrest the frequency drop in the system. And the lowest frequency that it can get in actually depends on the synchronously available the inertial support in the system. So hence a good inertial support system can actually make sure that this drop happens at a very small value and it doesn't allow you to drop too much, because dropping too much has a lot of consequences, which we will discuss. So essentially today's topic, we'll be talking about the time frame of anywhere between a disturbance happens in your system to a less than 10 seconds time frame where none of the actions such as the governors or the primary or the secondary or tertiary frequency control are coming into picture basically. Okay. And also we will discuss the ambient data, like for example, this data where the frequency will never remain constant because of the small changes in load and generation imbalance. And whenever that happens, always your dynamic equation will come into picture. Basically, we will see how best we will utilize this mechanism also to evaluate inertia, and as well as when a big disturbance happens, as shown here, the rate of change of frequency or ROCOF, what we call it as, is also very important, actually important aspect that needs to be studied for each system, each synchronously connected system. And then when the frequency goes, basically when the frequency drops to an extent depending on the inertia of the system, inertial support, it will come back later on, by using the frequency controls, the load shedding scheme and so on and so forth. And then area wise, you will recover the frequencies, which takes up to to minutes to hours actually in the system. And later on, spinning reserves are also coming into picture depending on what the operators wants to do to bring the frequency back to 50 hertz or 60 hertz. So this is an important concept actually based on which we will be talking today on the inertial response of the system. Now let's look at why do we need the inertia monitoring constantly or continuous monitoring of the system, why it is required. This is required because nowadays what is happening throughout the world, the penetration of renewable generation is increasing disproportionately. Okay, so as a consequence, there is a significant reduction of the inertia support for the system. Now, why I'm telling this particular point is that the electronics that are used in the wind and the solar and the battery backup systems, they do not provide any inertia to the system, even though the solar absolutely they don't have any rotational parts. So hence they cannot store energy, they cannot give back the energy. And let's take the battery backup system. Battery backup systems are also static in nature. They do not have any moving parts. Hence they cannot support inertia in the system. Now, in terms of the wind, even though they have capabilities of rotating masses through the big windmill it can store the kinetic energy, but unfortunately, the design is such that it is not allowed to put back its energy back to the grid. So therefore, none of these renewables which are integrated into the grid, are able to support the inertia of the system. Therefore, the penetration of renewable generation, as it is increasing, there is a huge concern of inadequate inertia that happens in the system. Now, what it means is, as I shown you in the first graph of how the dynamic response of electrical power system happens, you could clearly appreciate that the moment you have lower inertia, then it is also associated with the rate of change of frequency. Excessive frequency drop, if it happens, then under frequency load shedding and the protection under frequency protection relays will operate, and this may lead to blackouts, because if you're tripping lines which are heavily loaded in a system, then it will have huge consequences. For example, if you take away 1000 megawatts suddenly from a tie line that is flowing, and the consequences of such is, if the route of the topology of the power flow, if it is stable, then it can sustain. And in most cases, hundreds of megawatts changes are not a big deal in a big synchronous grid, but thousands of megawatts is definitely a big deal in a system where if you take them off suddenly, then you will have consequences in the system. So therefore, it may lead to the blackouts and other things. There are cases actually that has happened in practical world, and therefore it's very important to make sure that you estimate the inertia as closely as possible in real time or near real time, to make sure that the stable operation of the grid and enough spinning reserves are available to secure your operations. So if you look at the North American Electrical Reliability Corporation's recommendations and guidelines, they have standards, which is called as NERC BAL 003-1, which requires sufficiently, higher frequency responses from balancing authorities. And it also has a group called as the Essential Reliability Service Task Force, ERSTF. So they have three important measures to look at as a metric to find out the inertial response of the grid. And they are as stated in measure 1, which talks about synchronous inertial response at an interconnection level. Okay, that means if the two areas like north region and south region, or south and west region, east and west region, and so on and so forth, is interconnection of two different areas. So you should make sure that your inertial balance is there and in those areas when you exchange the power. And then initial frequency deviation following a large contingency. What we mean by large contingency is taking away larger generators off from the system, or taking away larger loads from your system. So they are all larger disturbances that happens in a system, or a big fault that happens in a system. Okay. And then thirdly, it's a synchronous inertial response at a balancing authority level. So balancing authorities levels are nothing but, inside within India, it is very similarly, you have areas where you have enough generation and load, and you can basically balance area wise, where you generate some megawatts, and then you also have the loads that needs to be balanced out. So they can be classified as each area basically. In your in India, basically the southern region, the northern region, the eastern region, these are all regions. They inside that they will have a capability to balance load and generation basically. So these are some of the guidelines that are available, and therefore real-time inertia monitoring will help in validating these guidelines. Basically, once the guidelines are set up, you have to validate them because of the changes in the electrical power system structure. Every day they are changing, and huge amount of solar is being added in India. In India, the one good thing is, because the grid is highly synchronous at this point, the north, south, east, west, everything is joined as one grid. There is a huge support of rotational mass that is available in the system is still helping actually the grid to not to take the frequencies to a very worst level at this point. But in the future, because of the continuous growth of solar and other penetrations within India, you will have a bigger problem with inertial support of the grid. Let us see this, in reality, how this has happened in the recent blackout problem with August 9th, 2019 UK blackout. Now, UK blackout actually, even though inadequate inertia was one of the major contributing factors, but the reason that this blackout started was because of a lightning strike at two big generators. Approximately the combined generation was around 2000 megawatts. That was suddenly off, and then at that time the distributed energy generation or the renewable generation was around 35%, around 700 megawatts of wind and solar were there, and there was no support from them for the inertia for the reason which I explained, because of their electronically made devices, or they are not allowed to put back their kinetic energy back into the system. In case of wind, you will have zero inertia support actually from the grid. Now, because of that, what happens is the rate of change of frequency goes down. As you can see, the rate of change of energy as the frequency has come down to such a level at 48.889, where it operated basically the under frequency protection in their system. So the frequency drop was in excess of 125 millihertz per second, which is the ROCOF, which fell very fast. And the under frequency load shedding operated at 48.8 hertz, which was affected about 1.15 million customers. Now, as a consequence of this, the Great Britain appointed a task force to assess the inertia response of frequencies using synchrophasor data, because they wanted to know if the changes of dispatch and renewables are connected to the grid is changing rapidly by the very nature of availability of the fuel, which is the sunlight and as well as the wind in this case. If they are very variable, and the forecasting of that system is even a very challenging thing even today. So therefore, it's important for operators, system planners, protection engineers to understand the inertial response of the modern grid with embedded generation such as wind, solar, or battery backup and small hydro plants. And so let's understand the inertial response of modern grid, in a much exemplary, aspect, which I'm taking the North American interconnections, the three big interconnections of North America, which is the Eastern Interconnection, the Western Interconnection, and the Texas region. So these three essentially are, even today, they are operating because of the back-to-back DC connectivity. They are isolated by themselves. And within that, you can see that by 2050, the renewables in each region actually is growing, is so high that by 2050, the 70 to 80% of their generation comes from the renewable in North America. And similarly, in Western region, it's around 60 to 70%. Now, when this happens, as I said, this means that within each interconnection like this, there will be a electronic coupling of various solar and wind generations and battery backup, and therefore there is no inertia support. So therefore, what happens is, within each region, there's a drastic decrease, and the rate of change of frequency will become very high, and then the frequency drop will be much below the nadir point, which is the minimum point where the current protection systems operates. So therefore, this calls for re-evaluation of the current regulation limit, under frequency and over frequency, and other aspects continuously monitoring the grid, because we cannot just say, okay, we evaluate by looking at the inertia constants of all the machines, which I will tell you actually currently how we are evaluating the inertia constant. Now, in the future, because of this variability of the generation, it's very important to measure this inertia in real time. So looking at the inertial response by interconnection, for example, in this case, for a given disturbance, you can see that the Texas is shown as is in green color, and Western interconnection is shown in black, and Eastern connection is shown in blue. You can clearly make out there is a huge support of rotational mass in Eastern connection, compared to Western and compared to Texas. And in Texas region, because of higher penetration of wind and solar, you can see that already the frequency is dropping to a very low value. And there is a NERC recommendations actually in North America that it's called as interfrequency regional obligation, IFRO limits. And the limit actually for each one of the regions is stated here. And the negative sign is because of the generation loss. So 1015 megawatt per every 0.1 hertz. If you lose 0.1 hertz, if the frequency drops by 0.1 hertz, you can lose only about 1015 megawatts in Eastern region in order for it to operate stably. That's the meaning of IFRO. Okay. Likewise, if you take ERCOT, only 425 megawatts, if it drops for every 0.1 hertz drop, you should make sure that the grid is stable within these operations. If it goes below this, that means there is a danger for ERCOT stability. So therefore, these things are very important. I know, as I said, like if you have more inertia in the system, obviously you can support such loss of megawatts, through the rotational kinetic energy that gets back the power to the grid. But if you have more electronics such as renewables, then obviously the total power, is contribution of power will be higher because of this penetration of solar and wind. And once they go off from the grid, then you don't have any support of inertial support equivalently from the system, such as the wind and solar, and therefore you will have problems of dropping your frequency below a very marginal the level where the protections and stabilities are sacrificed in the system. So coming to the four important metrics of impact of low inertia in the system are as follows. The first important thing is the frequency drop. So why the frequency drops, as I told you, when the generation actually goes out, that means you're not supporting enough load. When the loads are not supported, since the system is synchronously connected, every generator tries to adjust its speed in such a way that it tries to meet the loss of generation with the same amount of load that is there in the grid, and hence the only physical phenomena that can happen is the slowing down of the generation. So therefore the frequency must drop. Okay, so in case of the loads remain same, but if the generation goes off, the frequency has to drop, which is very large value in case of non-support from the renewables in the system. And likewise, the rate of change of frequency, ROCOF, will go very high because it drops very fast in the system. So that's the second metric. The third metric is critical clearing time that is available for a larger line. What do we mean by this is that, for a given line, say, for example, 500 kV line carrying 1000 megawatts of power, or the thermal above it's within its thermal limits. And you should make sure that when a fault happens, you should clear the fault in a particular time frame. That is called as the critical clearing time. If you do not do that, then either the transmission line will melt down, or the stability of the system is affected, or both can happen in the system. Therefore, it's very important to look at these parameters, carefully. Now, this will be lowered because of the reduction in the inertia in the system. And the fourth and the most important one is the natural oscillations of the system characteristics will change if the inertia of the system changes, because the inertia of the system is related to the natural modes of oscillations of the entire generator mass. Imagine that India is such a huge grid, and each huge grid is made out of large number of set of generators. And if you take each generators actually and then combine all their inertia, it's a huge mass that is available in the system. And now, because of the non-availability of the inertial support from the renewables, the way with which the synchronous grid operates is entirely different. So it'll probably slow down, or it'll pick up the speed depending on how much of inertia support is available to the grid. Therefore, oscillation characteristics of the grid changes. Let's take a quick look on each one of them, how it's going to impact. For example, here, the renewable generation is high in case 1, and in case 13, synchronous generation is very high. So when the synchronous generation is high, obviously you will have better support from inertia. So synchronous generation is high in case 13, and therefore, the curve will go up in a safer region. It operates in a safer region. Now, when the inertia comes down because of the renewables are going high, see, look at the way the traces are coming down on the rate of change of frequency. Also, we will look at it. It goes very high, and the frequency will drop to a much lower value. And because of this, there's a danger in the system, and therefore the frequency should never drop below a certain limit that is as planned in the system or as regulated in a system. This depends on system to system, basically. So monitoring these things in real time is an important aspect, as I said, because of the variability in generations, and the support of inertial support is not available because of the renewables. Now, let us look at how it impacts the rate of change of frequency, that is the rate of ROCOF frequency. Now, in case 1, as it is shown here, when you have all synchronous generation, you can see that the frequency is dropping only 0.45 hertz per second. And if you have 80% of synchronization generation and 20% of wind, see, frequency is already gone high, the rate of change of frequency, 0.56 hertz per second. And if we change the role of the synchronous generation to only 20% and wind and solar to 80%, you can see that the ROCOF goes to a very high value, and this value is not acceptable as of now because of the instability and the protection system that operates and load shedding scheme operation happens. And all these things are calculated using a simple formula, as shown here. And you can see that here, with number of wind generation, this whole thing will become 0 because the inertia of support of renewables is 0, and therefore you can see that dF by dt will go up for a given number of the wind generation or the solar happens, then there is no support from them, and hence for the imbalance that happens in the power, and therefore dF by dt has to go up. There is no other go, basically. So therefore it impacts the ROCOF of the system. That is dangerous. And thirdly, let us see how the critical, because you look at the variables, the critical clearing time is directly proportional to H. When the H decreases, your TC, the time for critical clearing time, also decreases, and you can see the curve getting into unstable region already in your system. And therefore, the lower critical clearing time reduces the transient stability of the synchronously connected grid. And the oscillation changes, as I said, NERC, through NERC report of the interconnection oscillation analysis that was done in July 2019, very recently, The changes in, look at the change base simulation was done in using the inertial support, which is 204.8 gigawatt seconds basically, and it was reduced to a smaller value from 204 to 191, and you can see the natural frequency has changed from 0.72 to 0.79. Now it may appear that this is not a big deal, because what is the problem with 0.72 and 0.79? But recently, when in January 11th of 2020, we had a big oscillation event in North America, and the disturbance that happened actually in Eastern Interconnection, Eastern side, was completely actually, it was transmitted along the entire Eastern region. Basically, in the oscillations of up to 200 megawatt was observed on the tie lines. Only there was a problem of 20 megawatt in one of the generators that happened in Florida. But this happened because of the phenomena called as inter-area resonance. So in the inter-area resonance, what happens is the natural mode of oscillations, if it coincides with one of the natural frequencies, as I have shown here. For example, instead of if the disturbance that has happened had a frequency of 0.72 hertz, it would have caused a inter-area resonance here. Now, since the inter-area resonance has moved because of the non-inertial support to 0.79, now 0.79 hertz disturbance can cause inter-area oscillation, which is very dangerous, because under resonance conditions, the value of the megawatts that flows in the tie lines can go by a factor of quality factor, which depends on the kind of resonance that happens in a system. It can be a multiple of 10 times or 20 times that of the actual disturbance that happens. For example, if a 20 megawatt generator has some disturbance of 20 megawatt, and this 20 megawatt will appear as 200 megawatt in the tie lines, basically. So this is the kind of danger that happens. That's why it's very important to monitor these things in real time, to see that if there is a change in oscillation characteristics, then you should know what is the amount of change that has happened and what are the natural frequencies that are disturbed. When you have a disturbance in your system, what is the forced response, which is very close to this natural response, which can cause inter-area resonance. So what is the current practice actually of inertial calculation? Now, currently what they're doing is that they estimate the inertia based on the information from EMS and SCADA. So the SCADA, what happens is every 10 seconds or 20 seconds or 1 second, depending on the kind of SCADA what you have implemented, they get the information of the generator breaker status. That means all the synchronous generators which are connected in the system, they get the breaker statuses and they include their inertia constant based on the design value. So as you can see, first of all, we are making a mistake of, utilizing the design value. It may not differ too much from the practicality, but when it is put into the system, obviously, and then everything, all the rotational masses are connected to the shaft, there will be some variations actually from the design value. And that is one aspect. The other aspect is in most cases, actually, since we take only the generators breaker statuses to include for the inertia, we are forgetting about embedded generation such as the wind, solar, battery backup, and other rotating devices that are there in your system, such as synchronous condensers, big induction motors, which are having very high impact of inertial support to the grid. Now, all these things are not considered in the current practice. Now, with the measurement mechanism through synchrophasor technology, you will be including all these aspects actually into the system, and therefore a measurement based inertial response estimation is always considered superior compared to the estimation that is currently done. And we also assume that currently that there is a really linear relationship exists between system inertia and demand variation, which is not correct basically in terms of the practicality if you take. And therefore, there are a lot of assumptions we make currently. Now, why real-time inertia monitoring using synchrophasor is important? We'll have to go through some definitions first of all in order to understand that. For example, inertia is a time-varying quantity. Don't mistake that. When a machine is designed, its shaft and the moment of inertia is fixed. And where is the question of varying of inertia coming to picture? Here, what you have to understand is the inertial contribution of each generator is different. That means each generator is this. But there is a total system inertia constant that is available in a system because of the contribution from various generators at a given point in a synchronous grid. For example, if you measure the response, synchronous response or the dynamic response very close to an intertie or a tie line where there is no generation is available, basically, it doesn't mean that there is no inertial support there. So the inertial support is a combination of various generators at that point. So this is area-wise inertial response. This is what we are talking about is varying because of various dispatches that happens in a system and non-support from the inertial support from the renewables. All these things have to be considered. And inverter-based systems, as I said, doesn't support inertia or provide no inertia. And wind, even though they have rotation mass, they cannot support inertia because the very way it is designed as of now, is not to support inertia. But there is a concept of virtual inertia and other things. And this presentation, I'm not covering the mitigation effects. So let us understand the concept first, and maybe in the time permits in the future, we can talk about what is the virtual inertia and how do you mitigate this inertial issues that happens in a system and so on. Now, individual generator system inertia, as I said, it can remain pretty much constant because of the way the rotational mass and other things are designed basically. But when it comes to total system inertia and the inertia of area-wise inertia, these are all variable quantities that you have to understand. That's the reason why we need to determine the system inertia at the high speed with the high speed time synchronized data such as synchrophasors, which is highly suitable to monitor the inertia of the system. Now, high resolution time synchronized data availability, how it is useful, how synchrophasor technology can provide the evaluation of inertia in real time. Now, if you look at the way the synchrophasor technology works, the most important thing is it's a common time frame. Okay, the common time frame is available for all the areas. For example, eastern, western, and the ERCOT region in United States. For example, a similar example you can take for India. Southern, western region, eastern region, and so on. Now, let us suppose that each one of them have inertial impact. This is the combination of all the generators. Let us suppose you have this information. And because of this technology, synchrophasor technology, since it has a common time frame reference with which the various quantities such as the voltages and current phasors, everything is measured, the physical phenomena that is happening, that is the dynamic response that is happening in any of these region at a given point, can be evaluated at the same time, and you can come to a conclusion of evaluating these variables and getting the results out of this has a lot of meaning. It is simply like this. Let us suppose that you have 3 regions and it is connected by a transmission line, and let us suppose that at this point you want to look at the currents that are incoming at this node or at this particular region is the current that is some of the currents that are incoming through Kirchhoff current law, and this is valid only if you take every instant of time. That means I of t of incoming must be equal to I of t of outgoing, basically, right? So the thing that is common here is T. T, that means at that particular instant of time. This is what the capability of synchrophasors can measure the quantities such as voltages and currents very precisely with their phase angles at a time with a discrepancy of few microseconds basically. So therefore, the physical system, when you are trying to evaluate, it is very suitable. All these dynamic equations, the equations that what we follow actually in power grid, all becomes very meaningful. And therefore, synchrophasor technology is very, very suitable, to evaluate the inertia of the system. And now the benefits, other benefits of using synchrophasor measurements is as I said, it provides time synchronized measurements over wide area of the grid. And it provides high resolution data. That means the resolution of today's SCADA is in tens of seconds. But whereas in synchrophasors, it can give you the insight into the system. At every 1 second, you will have 30 such phasor information every second. So that means it could be in 10 seconds, it could be 300 times more than what the current SCADA is measuring. So that means it's kind of comparing MRI with the X-ray, right? So in X-ray, what you can see is to a certain depth, but in MRI, you can get to a level where you can really look at the depth of the neural systems and other organs actually to a level where you can come out with a lot of analysis on exactly what is happening in the system. And in a similar way, analogous way, the synchrophasor data will allow you to really evaluate various phenomena that happens in power systems. Okay, so it does not suppress the events, the significant events and phenomena that happens in power systems, whereas the SCADA data, it is possible that we will miss a lot of important functionalities such as oscillations and other things. It's very good for steady state conditions, but not for dynamic operations. For dynamic operations, it's very important to look at synchrophasor measurement. And the rate of change of the frequency, which I told you the significance for associated with inertia, is directly measurable from synchrophasor data. It comes as a quantity through the protocol itself, standard protocol itself. So it's available to you. And time synchronized phase angles are readily available for online estimation of inertia constant. So therefore, these are some of the benefits of using synchrophasor technology compared to the SCADA technology. And the approach, actually what we have done is, we will take the real-time inertia area-wise inertia constant using wide area synchrophasor measurements. That means essentially what we have to do is we have to divide the bigger synchronous grid into several areas. So when you divide them into several areas, you place the PMUs in those areas which are of interest to you, and then you measure the disturbances and then evaluate based on the dynamic equations, okay, inertia constants. So there are several methods which I will discuss. Actually, one of the two most important methods which utilizes the disturbance based methodology and as well as using ambient data. That means the normal synchrophasor data itself can be used in real time to evaluate real time inertia based on the sampling of the synchrophasors. So once we do that, then we evaluate the total inertia constant using individual area constant. So we add them up basically in a manner which I showed you in the equation, and then we determine that. Once we determine individual area, we'll determine the area wise kinetic energy reserve and estimate the total kinetic energy reserve. See, this is important because you have to understand that in a synchronous grid, the entire grid, for example, in India operates at one frequency, means we have to look at the overall contribution of the kinetic energy support in the entire grid. It may be the support may be coming from east side or the west side or the southern side, it doesn't matter. But since they are all connected, synchronously connected, the entire set of generators which are there in these areas will act and try to support the inertial support it will give under various disturbance conditions, which we just described actually in using my initial response, the curve which I showed you. So it's very important to look at the real-time visual display of inertial response summary for the operators to get an idea of what is happening in their entire grid and what is the amount of the spinning reserves that they must have, what are the kinds of battery backup systems that they must have to support the system, and so on and so forth. So these are the important outcome of the approach of calculating the individual area and then the total area inertial support for the system. Now the current project what we have developed, actually it is done in 3 phases as shown. The first phase is completed where we have done the simulations with known benchmark models to develop a robust technique for estimating inertia constant. And the phase 2 is planned now where we wanted to utilize the real field data to tune the algorithms. And the phase 3 is the prototyping development for commercial utilization to implement the real-time visualization, to implement the logic of the system, to provide operators with inertial situational awareness. See, for example, today, if you use the synchrophasor data, so situational awareness is coming from measurement of phase angle of the system, because in a power system, in AC power system, bulk AC power systems, the phase angle is directly related to the stress that is happening in your transmission system. What do I mean by that? If you take your equations P, equal to V1, V2 divided by X times sine delta, where delta is the difference in the phase angle between the two ends of the line. So more in power systems, V1, V2, X are pretty much constant or controlled. V1 and V2 are controlled, voltages are controlled, and X is constant in your system. Therefore, the power flow is directly proportional to sine of delta. And that means the phase angle is, if the phase angle is more, the power is more, the phase angle will be higher in electrical process. This is a very simple relationship you must understand. So when there is a stress, what do we mean by there is a stress? That means the phase angle when it increases in the system between the two ends, that means there is a higher power that is flowing in the system. So when the higher power flows in the system means higher stress that is happening. It could be a thermal limit, it could be a stability limit. We have to evaluate all that, right? So what I'm trying to analyze here is that the amount of the inertial situation, the situation in situational awareness for the current systems is measured by directly the phase angle measurement that what we are doing through the synchrophasor. In a similar manner, in a very similar manner, the inertial situational awareness also can be plotted very similar to this power equation. We can evaluate the H inertia continuously of the system, and the operator can look at the situational awareness of the inertia. That's what we are trying to do in the third phase, basically, to alert the operators with alarms when the inertia goes below certain threshold limits. So in this, actually, what we are trying to do is, one is the moving window method, which I will describe, through which we will evaluate the inertia of the system area wise or each individual generator using the disturbance measurement methodology. That means whenever a disturbance happens, this method can be applicable using the synchronous. Now, when there is no disturbance, continuously when the system changes its topology, or when the dispatch of renewable changes, then there will be some variation in the system, and with the measurement, usual ambient measurement of synchrophasor data, we have come out with a second technique which uses ARMOX methodology technique, which uses the system identification, and through system identification we will evaluate the H inertia of the system. So those two methods I am going to describe now. Now in the first method, as I said, the dynamics of the system equation, of course, we have made some assumption here. The damping and other things are neglected, which is a fair assumption to get some, more conservative results. But it's an absolutely viable assumption. And if you take that and look at the way you evaluate H, the inertia constant, and the total inertia constant, you can actually evaluate whenever a disturbance happens in a system, identifying the disturbance starting point. As I said, there is the only support that is available to the system during that time is inertial support. Therefore, the evaluation of H will be pretty good in that region of below 10 seconds. Okay, so this is the method what we have followed. On the left hand side, there's average value we have found for each selected time window, which is a movable window, when there is a change in delta P that happens when the disturbance happens. And similarly, the ROCOF also is another quantity that we evaluate actually when a disturbance happens with the same time window. Same time window is applicable for both. And now defining time window of length time T, H is calculated like this, basically of the system. So we have done the study for the Western system interconnection with the 3-machine 9-bus system. It's a Western connected system, which is a reduced system basically, which has 3 generators and some transmission lines and loads and so on. And you can see that inertia constant of each system is 23.64, 6.41, and 3.01 seconds respectively based on 100 MVA. Now, with this method, actually, what we have calculated actually the inertia constant of generator, which is the generator 1 of the system, which is close to 24. So we have obtained our results very close with a very good accuracy using 4-second time window. Basically, that means you set a 4-second time window and evaluate the dynamic equation and move the window for every sample of the synchrophasor data, depending on the sample rate of the synchrophasor data, and then evaluate the value of H. That's what we have done on that. So if you look at the estimation of inertia with a window length of 4 seconds and look at the average power and the variation of average ROCOF, and this divided by this essentially will give you the value of H multiplied by the system frequency, which is as shown. So you can see that the value will converge very nicely over a period of time. Within 10 seconds after the disturbance, the value is converged to a value of 24, which is very close to 23.64, which is very close to 24, which is the design value of the inertia of the system, which is within 1% of the actual design value. Now, estimated inertia for other generators and the total inertia is also shown here, which also basically agrees upon very well with the with the window second of 4 seconds. Now we also did analysis actually taking the measurement at different frequencies at different points in the network, and all of them actually still showed a very good agreeable inertial response of the system. See, this is exactly what I was talking about. Like if the impact of frequency, if frequency is felt everywhere in the system under the conditions that the system is operating synchronously, and the system is in dynamic and quasi steady state, the frequency is pretty much similar in all the places. The frequency is pretty much the same. Now, when a disturbance happens, that is where the frequency actually move as a wave, like a transmission, traveling wave. It moves from one region to another region till it attains the disturbance goes off. And after once the disturbance goes off, the frequency will be again constant and remains at a within a specified limit and in the entire synchronous grid. Okay, so this shows that the evaluation of H at different location also is very accurate. And now with the previous data, what we calculated was at a very high sample rate of 200 samples per second. We reduced the to practical PMU, what it is measuring today, And still we have very good results. Actually, you can see that for the 3 respective generators based on their own MVA rating. So this is using the PMU data with the same 30 samples per second. So the key considerations are measurements closer to each generator location or the area wise, if you look at each area, and accurate detection of event, which is of the duration of the event and the starting point of the disturbance is important. And the data quality of the PMUs have to be observed very closely to do this, to implement this method. And the selection of time window and size also has to be done properly. So these are some of the key considerations that in this methodology. And as I said, we also tried with different time windows, and pretty much most of the time window length does not really impact very badly actually on the results. So many windows such as 4 second, 8 second, 10 seconds we took, and then pretty much 4 second was considered as pretty good actually for the disturbances like this. So that's how we came to some conclusion. But as I said, this is a real R&D work that is still going on, and we have to prove a lot of these results with the practical data also. And the system identification method is done by using similar assumptions, saying that we started from a model basically in a system, and then we look at the inputs and outputs basically of the system, and then try to identify the model in between, and then utilizing the model you try to evaluate the value of inertia constant. Okay, so we use um, the autoregressive moving average exogenous technique basically to look at the polynomials in this forum, and then basically we are modeling the power systems using RMOX model with order n, and then slowly reducing the order basically to an extent where we take the set of inputs and make some assumptions, take the output as the frequency. That means the variation of the load and generation is what is important actually. When does the frequency change? When there is a mismatch in either the load or the generation. So that concept is taken here in order to evaluate the inertia of the system. Now, how do we do that? We first of all look at, as I told you, the measurement frequency can come from different places in the PMU depending on the position of the PMU. But still you can evaluate the center of frequency using a technique as shown here by giving proper weightages. In our weightage, what we have given weightage of 1 for all of them basically. And the aggregated frequency is calculated as the frequency of what you calculated on the system frequency, Fn. So when the delta Fij is found, then it is used, using the 4-step methodology here. We will convert the discrete model of RMOX to a continuous domain model here to look at the frequency response. Now, why do we do this is because we reduce the system in such a way that we will get the H, which is the system inertia, a constant of the system, is nothing but the impulse response of the system by reducing the system order. Now, the effective inertia constant is found by the impulse response of the system. So this is how it is calculated using the continuous measurement of synchronous data. See, the biggest assumption what we are making here is the frequency of your power system will never remain at a steady value of 50 or 60 hertz. This always varies. If you look at 50.002 decimal places, it may remain same. But if you look at third or fourth decimal or fifth decimal, always it will change basically. That means there is always a change in the load imbalance in your system, which can cause this issue, and that is what is essentially taken into consideration in evaluating through this methodology. Okay, so we have done the similar case studies for the system, the same system we have taken, the WSCC system, which is reduced to a 3 generator system with various buses, 9 buses. And then we have evaluated the random load variation we have done, and the input and output are calculated as per the equations what I described. It is implemented in a MATLAB environment, and then we have obtained the results very close to, the 6.41 is the theoretical value, but we got 7.19 because, as I said here, this is the place where we have activated governors, control action. All controls are active in this methodology. So therefore, there is a slight difference in the evaluation of inertia of the system, basically. So we are still evaluating, this particular methodology with the practical data. That's what we are trying to do at this point. But this particular methodology has been implemented successfully on a Iceland country with fewer generation. It's been successfully implemented using the PMU data. The same technology has been implemented and same methodology has been implemented, actually utilizing that, and they have obtained excellent results actually using system identification methodology. So the recommended PMU locations for getting accurate inertial measurement is proximity to synchronous generators. It need not be at the generating station, but as close to the generation as possible is a good thing. And critical loads with a very high moment of the inertia support, rotational mass supports, and the point of interconnection of renewables. So these are important points of location where the inertial measurement has to be done using the PMU measurements. So in conclusions, monitoring real-time inertia allows operators to have situational awareness of frequency response of the rotational kinetic energy reserves. It allows operators to plan better generation dispatch. And the total kinetic energy reserve available will help for better forecast for minimum reserve necessary for stable operation of the grid. And it helps in re-evaluating the interfrequency response obligation. This may be with respect to NERC in North America, but this is also equally applicable to India, depending on the kind of, the index that what they are utilizing. So in summary, inertia constant affects the frequency drop of the frequency response. It varies with time. As I said, the effective inertia varies with time and it affects the grid stability, critical clearing time, and natural system modes. Real-time estimation of inertia constant benefits operators to plan better generation dispatch, user spinning reserves, and protection engineers to evaluate the ROCOF and under frequency and over frequency settings and so on. And synchrophasor data is suitable for real-time measurements of inertia for power system, which includes the contributions of embedded generation, loads connected to the system, renewables, etc. So with this, I'll just state the current status. What we have done is we have done the problem definition, approach and concept. Testing and validation is done on simulation, and what we are doing at this point is trying with real field data and then the prototype development, which will happen in a matter of 1 year. We are trying to look at these opportunities and making this as a commercially available tool. So with this, I would like to thank all of you. Thanks, Sambandhan, for providing me an opportunity to talk to you guys, and hopefully, this has impacted you in your research and other things. And now we'll open the presentation for discussion. So if you have any questions or discussion that you wanted to make, we can, I can take up the questions and we can discuss.
Dana, is there any in the chat box?
In chat box, no questions, sir. I request
Anybody
all
can-
the participants, if you have any questions, kindly unmute your audio and ask the question.
anybody has any doubts or questions or queries?
Well, I think they may be sort of formulating their whatever questions. They may send it through email. Maybe.
No problems, no problems. I mean, this is, as I said, it's very important to understand.
Absorb.
Technology, and then this is a slightly advanced topic, basically, but it's a good research and development topic. That's the reason why I chose this for a lot of PhD students and others. This is a very interesting topic, and this is a current problem.
There is one question in the chat box, sir.
Yes.
Can I ask, sir? No.
Yes, please go ahead. Yeah.
What are the challenge if the renewable contribution exceeds more than 80%?
That's exactly what I'm telling about. See, what happens is the biggest challenge would be, if 80% the renewables are there in your system, and only 20% synchronous generation is there, then there are concepts such as virtual inertial support that can be applied to the grid, because now you have a lot of controllable devices, the power controllable devices such as the inverter based controllers, so that they can provide and modulate the power, active power, so that, as I said in the equation, and if you go back to the equation, let me tell you how that is achieved. Basically, if you look at the equation, dynamic equation here, in this equation, if you look at the power that is basically within the inertial response, mechanical power will pretty much remain constant. It doesn't change. So only the electrical power from instant to instant changes. Now, if the only thing that on the left hand side, if you look at the df by dt, the frequency of the system, Fn and H is there in this system, right? H is your inertia of the system, basically. Now, in order for you to support this left hand side equation, what is happening there, you can basically balance out by right hand side quantities such as the electrical power that is input into the system during the inertial support. Now, when this happens, these powers can be very nicely contributed by the current, the devices, IBR devices, such as, even the battery backup. Actually, nowadays it's so intelligent that it can provide you extra power when it is needed into the system, and it can modulate the system power so that the inertial balance will be obtained, basically by providing virtual inertia to the system. It's nothing but the power balance, basically, right? What happens is when you lose generation, that means you have to basically support the load that is available with extra power, but that is whatever it is required. Now, this extra power is derived from some of these devices which still have the capability actually to generate. For example, if an inverter system is designed for 300 megawatt and you are operating only at 200 megawatt, then you still have 100 megawatt that is available to support the virtual inertia in the system. So that's how it is done. So if the moment the higher renewable penetration is there, techniques such as virtual inertia and other concepts will come into picture. Now, if I elaborate that question and then say what will happen if there is 100% renewable, then you don't have to worry about inertial problems, right? So that's what happens actually. A grid can be operated with no inertial support. Why not? If you do not have any inertial problem in a system, then system becomes very fast. A frequency response becomes very fast. Now, under such circumstances, what will happen? The philosophy of protection and other things what we are doing today, that needs to be adopted to the newer situation. But it is always possible to control these things and mitigate these things.
Sir, to sort of supposing if they operate different microgrids,
Right.
supposing they are all, the renewables independently in islanded mode,
Correct.
I think that may little bit lower down the problems of inertia.
Correct. You're right. But the issue is, if the microgrid is connected to, it has to be connected to some generation, right?
Yes, yes,
See,
yes.
no microgrid today operates without synchronous generation. So it has to operate. For example, where do you provide your microgrid power? It has to be provided to households, domestic, irrigation. So all these loads are still, they have motors and other rotational masses. Still, you need some support of the inertial support.
Yes.
So it cannot be totally independent. But that's where I'm telling, what I'm suggesting is there you will have to put extra generation capability through your battery backup and other systems, so that the battery can be charged whenever the fuel is available, such as the solar or the wind is available. You can charge and store the energy. That energy can be later on used as a spinning reserve to support the inertia of the system.
Okay. So battery storage is also more or less required. It will become mandatory.
Yes, it has to be. Otherwise, the whole thing will see. That's why in India,
collapse.
What is happening today, India is not seeing this problem because the penetration of renewables compared to the rotational inertial support that is available is great. So that whether it is from northern region or southern region or eastern region, all generators rotational masses are contributing so nicely. That's why you are not able to see this impact.
Yeah. That's right. Maybe, as you said, by another 10 years.
Yes. Another 5 years, Why 10 years? Because it depends. Like, for example, if a southern region itself has certain amount of generation and a certain amount of this one. So by the time the impact of rotational support from northern side hits the southern side, that time frame is very important. If it takes 1 or 2 seconds, then you're already dropping your inertial support, right? So it depends, it's a question of time, basically.
That's right. It's a very interesting topic, and really, you have woken up many minds. Really, it is a good area to a lot of researchers can get into it.
Yes.
Yeah, definitely. As I said earlier, we have a protection lab in our college with all the real-time, real relays, as if it is a real control room of any power station or a control station, a substation. We can take up your projects and do some experiments. And
Sure. Yeah. No, we'll work together. There are some interesting things. Like, that's why I said you need Phaser Smart tool.
Yeah.
So we will see how to get that tool into your system and so on, and whether through the project or whatever. I will ask someone from from PRDC to contact you.
Yes.
And we can start something. It's exciting, actually.
Yeah, it is exciting, definitely. This inertia problem, many people were totally, as you said, because in India, we have not felt that. Once it is felt, then people will rush to that. The synchrophasors.
That's why, if you look at the UK blackout, 2019, it has happened only 1 year back.
Yeah.
August, exactly 1 year. 1 year, August.
Yeah.
2019.
Okay. Exact. Yeah.
Yes.
Yeah.
Yeah. So you can see that there is a issue there, and they easily tracked that. It was not even 3% of their entire inertial support stuff, but they felt it locally. It operated actually their system, and the 1.15 million people were out of power.
Oh. Very nice topic, and I hope all the participants would have gathered the required informations, and we welcome everybody to be in touch with us also. We have a protection lab, and where we can study all those very crucial aspects. And along with Dr. Krish Narendra, we will definitely take it further. I invite everybody to come to our lab when the COVID restrictions are over, and have some insight into the whole area of protection and synchrophasors. Thanks a lot, sir. Thank you very much.
No problem.
You really, taken your effort, and it's so late in night there. It's now more than 11:30 midnight now.
No,
Really,
yeah,
thank you.
Almost tomorrow for me. No problems. Actually, I really enjoyed, and I mean, let us keep in touch, and there are other interesting topics, fundamental topics, and other things that we can definitely talk about, which I think which is important, and keep in touch. Thank you all for your support. Bye for now.
Thank you, sir.
Thanks a lot.
Thank you, sir.
Gayatri,
Thank you, sir. Gayatri ma'am?
Huh? Oh.
That is not proper.
Hello. Hello. Gayatri. Gayatri, you can conclude by giving a word of thanks, even though he has left.
Hello.
Hello.
Can you hear me, sir?
Yeah, I hear you. What I said is you can conclude the meeting and then tell about next meeting.
She has. Yes. Thank you, sir, for your valuable inputs to us and eye-opening inputs. Thank you, sir. Thank you so much.